Can you have a look at page 6 of the supplementary worksheet? Okay, page 6 of the supplementary worksheet. Okay, this is June 10 P41. Okay, the first part of the question asks you to define the radian. We actually did that before. So it is actually angle subtended at the center of the circle by arc length equal to the radius. It's just something that you can just copy off from the notes. Right. Now look at part B. B is the one that we want to talk about. Now, a stone of weight 3 Newton is fixed using glue to 1 MP of the rigid rod CP, as shown in the figure. The rod is rotated about NC so that the stone moves in a vertical circle of radius 85 cm. The angular speed omega of the rod and stone is gradually increased from 0 until the glue snaps. The glue fixing the stone snaps when the tension in it is 18 Newton. For the position of the stone at which the glue snaps, on the dotted circle of figure 1.1, mark with letter S the position of the stone. Okay, so what they basically mention here is this. You have a stone is glued to this rod. You're trying to swing it in a circle, and then when you swing it, you're increasing the speed with which you swing it. You're increasing the angular speed. And then at some point, at some value, when you increase the angular speed, the glue suddenly snaps. Okay, so they're asking you where would be the position where the glue snaps in this vertical circle. So just now I mentioned to you, usually the tension at the bottom is the largest. So where it snaps, it will usually be at the bottom. So it will snap right at the bottom, below the center. Okay, so this is where you want to mark your position where the glue snaps. Okay, so this is S. All right. All right, then for that same position where the glue snaps, they're asking you to calculate the angular speed omega of the stone. Okay, they want you to calculate out the angular speed omega of the stone at this very same position where the glue snaps. Okay, so let's consider this. At the bottom of the circle, which is this one, the forces that are acting would be the weight W, and then after that, you will have tension. Okay, so let's just say tension T right now, because I'm not analyzing top and bottom, so I don't really want to make any distinction there. I just give you a general term tension. So now, I know that this thing moves in the circle. My centripetal force would be, say, mr omega square here. Because I know that I'm using angular speed, I would just use mr omega square. Now, my centripetal force will be provided for by tension and the weight. The centripetal force acts towards the center of the circle is outwards right now. So T is positive, W is negative. I will get T minus W equals to mr omega squared. All right. So sum inside here and you should get your answer. All right. The weight is, sorry, the tension was 18 given here. The weight is 3 given here. Okay. So mass is not given directly, but you can work it out because W is equal to mg. So m is W over g. That's why you get 3 over 9.81. Then your radius is 85 centimeter, change to meter. So you will get omega as 7.6 radians per second. Okay, so this is one part completed. Okay, next one I'll go through again is a vertical circle that is more directly related to what we just did in the notes. Okay, this one, go back to the regular worksheet. Okay, go back to the regular worksheet, the one with more number of pages. Have a look at page 59. Okay, so November 2021, P42. Now, first question. State what is meant by centripetal acceleration. Centripetal acceleration is the acceleration perpendicular to velocity that causes circular motion. This is the most straightforward way of describing what is centripetal acceleration. Okay. Acceleration perpendicular to velocity that causes circular motion. All right. Then we move on to the next part. An unpowered toy car moves freely along a smooth track that is initially horizontal. The track contains a vertical circular loop around which the car travels, as shown. Then after that, they tell you the mass of the car is 230 grams and the diameter of the loop is 62 centimeters. Assume that the resistive forces acting on the car are negligible. Now state what happens to the magnitude of the centripetal acceleration of the car as it moves around from loop X to Y. It moves around the loop from X to Y. What happens to the centripetal acceleration? Okay, so let's consider this. This one is moving in a vertical circle, right? If you're moving from X to Y from here to here, you consider the energy changes again. GPE is increasing, so KE is dropping. Okay. So in your case here, as you move from X to Y, GPE increase, KE drops. That means your velocity is dropping here because KE drops. Now, if you recall that SC is mv squared over r, if m and r constant, that will mean that FC is proportional to v squared. So since v is dropping now, FC drops. Okay. And also, you know that in general, FC is mass times centripetal acceleration, right? So if FC drops, AC will drop, okay? So here, velocity drop, AC drop, therefore AC drops. So the magnitude of your centripetal acceleration decreases. This is the logic or reasoning behind it. All right. Okay, so if this one is okay, then I'll move on to the next part. Okay, right. So I move on to the next part, which is at the bottom here. Now, the next part they ask you, explain. Let me just get it. Explain if the car remains in contact with the track, why the centripetal acceleration of the car at point Y must be greater than 9.8 meters per second square. Okay. If your car were to remain in contact with the track at point Y at the top of the circle, why would the centripetal acceleration be greater than 9.8 meters per second squared? All right. Now, when you look at this value of 9.8 meters per second, this value looks very familiar. All right. This value looks like the value for gravitational acceleration, 9.81 meters per second square, right? So this 9.8 is not a coincidental value, is somewhat related to your gravitational acceleration. Why is this specifically this value, right? So let's just consider a few things first, all right? Now, when your car or whatever object it is able to move in a complete circle like this and remains in contact with the track throughout, you consider some of the forces that act on the car. At the bottom position, you will have weight downwards and reaction force upwards. At the top position, you will again have weight downwards and also reaction force downwards. So at the top position, your centripetal force would actually be R plus W. But at the bottom position, your centripetal force would be R minus W. Okay. Now, we know that centripetal force must always be provided by the existing forces. You consider this now. If I talk about the top position, and somehow I say that the only force acting was just W, okay, and my centripetal acceleration being downwards towards the center of the circle. If my only force acting was just the weight, that would mean that centripetal force is equals to weight. Okay, centripetal force is provided only by the weight. And then after that, Fc is mass times centripetal acceleration. Weight is mass times gravitational acceleration. So the masses will cancel off. Right. The masses will cancel off, giving me the conclusion that AC is equals to G. Right? Now you will only ever get centripetal acceleration equals to G if the centripetal force was provided only by the weight. Okay, so that's why I wrote here, if centripetal force is provided by weight only, then the centripetal acceleration is 9.81 meters per second squared. But this situation is not possible. Okay, this situation is not possible. Okay, because the object cannot complete a circle in this case. All right, this situation is not plausible. It doesn't happen. All right, because the object won't be able to complete a circle in this case. All right, if the object was able to complete a circle, is able to complete a circle, it will experience a reaction force from the track. Okay, so if the object is able to complete a circle in the first place, it actually will experience a reaction force from the track, because that would mean that because if you are able to complete a circle, your object is in contact with the track the whole time. So because it's in contact with the track the whole time, it must have a reaction force. Okay, so in my case here, my Fc will be W plus R, which is what I'm actually, which is actually what I wrote here. So Fc now is W plus R, therefore AC will be more than G. Okay, you will only get AC equals to G if Fc is equals to W. All right, but this one I mentioned to you won't be possible because it won't be able to complete a circle. But here they say it's able to complete a circle, it remains in contact with the track, so it must experience a reaction force. If it experiences a reaction force, Fc is W plus L. So AC therefore must be more than G. Okay. So that's why the answer was this. To remain in contact with the track, contact force from the track is required. Thus, centripetal force is greater than the weight of the car itself. Therefore, centripetal acceleration is greater than 9.81 meters per second squared. All right. Can? So far, can get, right? Right, okay, so this one is okay, then I move on to the next part. Okay, so just bear this in mind first, all right? Your car right now is able to complete the circle, it remains in contact with the track, but to be able to do so, its centripetal acceleration must be more than 9.81 meters per second squared. So the next part is where they ask you about this right now. They actually want to make use of this information that you've just deduced. They tell you the initial speed at which the car in B moves along the track is 3.8 meters per second. Determine whether the car will be in contact with the track at point Y. Show your working. So here just now they tell you this is your track. And then they tell you your car was moving at 3.8 meters per second square. Okay, along the horizontal track with this initial speed. But because your track is frictionless in the first place, you can also just say that, oh, when your car reaches the bottom of the circular track, it will also be at 3.8 meters per second. So this one is your position X. Then it wants to go up to position Y. So the question is asking you right now, with this speed of 3.8 meters per second, would your car be able to move to Y in the first place? Would it remain in contact with Y? Would it be able to complete the circle? Would they still remain in contact at Y in the first place or not? Okay, so they want to know whether would this speed be sufficient. Okay, so this one kind of relates to what we just did in the notes. All right, so here we can just consider this using conservation of energy. As the thing moves up, I know that GPE will increase, KE will drop. Okay, so change in KE is equals to change in GPE. So change in KE is just the kinetic energy at the bottom, half mvx squared minus kinetic energy at the top, half mvy squared. So I already explained to you why is the bottom minus the top, because bottom is usually the larger KE. So half mvx squared minus half vy squared, mvy squared equals to mg delta h, right? Your delta h is obviously just going to be this part here. Okay, so this one is your delta h. All right. So now here, before you proceed, you can see that the masses will cancel off, giving you Vx squared minus Vy squared equals to 2gh. So you sum in the value for Vx, or 3.8. Then after that, you sum in the other values also. 2 times 9.81 times 0.62. This is actually twice the radius value. The radius was given as r equals to 0.31 meter. Okay, so double of that is 0.62. So eventually you will get your Vy as this, 1.51 meter per second squared. So now here, this is the velocity at y. They're telling you right now, velocity at y is actually 1.51 meter per second. Now here at this point, you want to find out what is your centripetal acceleration at that point. So at point y, centripetal acceleration is v squared over r, 1.51 squared over 0.31 over your radius value of 0.31. So your centripetal acceleration at the top is actually 7.36 meter per second square. Now, just now we already established that in order for your car to complete the circle, to remain in contact with the track, your acceleration must be more than 9.8 meter per second square. But right now, the actual one that you're having with the actual speed right now is 7.36. It's actually less than the 9.81 value. So here we can come to the conclusion, it actually doesn't remain on track then, because the question before we already established that it must be more than 9.81 in order for you to remain in contact with the track. So if it's lesser right now, the actual value is less, it won't remain in contact. Okay, so this is one way of doing it. This is actually the more straightforward way of doing it. If you try to do it like we did the notes, it's also possible, just that it may be a bit more tedious. That one will be shown below here. Okay, this one is a bit more tedious. We can do it the same way also, all right, if you wanted to. So this one, the workings here is actually following exactly what we did in the notes. So let's just consider this at point y. This one is another one again. Okay, I'll just show it very quickly for you. So this one is where my masses are at the top and bottom. At the top, I would have W, I would have R. At the bottom, I would have W and I would have R. So this one was point Y, this one was point X. So if we look at this one now, at point Y, W plus R equals to MVY squared over R. I know the car will start to fall, it will start to lose contact with the track when R is 0, when I no longer have any reaction force. So this one becomes 0. I will get W mvy squared over R equals to mg mvy squared over R, where vy is square root gr, where square root, so here I sub in the value, square root 9.81 times 0.31 will give me vy equals to 1.74 meter per second. So this is the speed that I will actually need in order to remain in contact with the track. Okay, So now from here, I want to work backwards and find out what is the speed required at the bottom of the track in order for me to complete the circle in the first place. So just on this one, I know my Vy now. I want to find out what is my Vx. So at point X, apply conservation of energy. Loss in KE is actually equals to gain in my GPA. So simplify, Vx square minus Vy square equals to 2GH. So Vx square minus with Vy square, the Vy that I use here is the Vy that I found here. So this one is minus 1.74 square equals to 2 times 9.81 times 0.62. My Vx is 3.9. This is the minimum Vx required to complete circle. But then now you compare it with the actual one. The actual one is 3.8. This is what the question told you. This is your actual value right now. But when you calculate it out, to be able to complete the circle, you actually need 3.9. Okay, so since your Vx required is actually more than 3.8, the actual value right now, your car does not remain on track. Okay, so this is another way of doing it lah. But this one is, I think, yeah, more tedious lah. Okay, more steps, more workings. This one also works, but this and this one is directly related to what you just did in the notes. Okay, so use which one you like, no? All right. But personally, I'll do the first one, no? All right, since it's the simplest one. Okay, all right. Then the next one would be this one. Okay, so let me just fill out certain things. Right now for D, they'll ask you right now, suggest with a reason without calculation whether your conclusion in C would be different for a car of mass 460 grams moving with the same initial speed. Now, before this, your car had a mass of 230 grams. Okay, if you read the question before this, the earlier part, they told you that your car has a mass of 230 grams. So right now, they tell you, what if I change the mass to 460 grams now? And the car is still moving at 3.8 meters per second squared. If the mass is now double, but the speed is still the same, would my car still be able to complete the circle? Would it still remain in contact with the track at the top? So the answer is that yes, it will still remain in contact. It makes no difference. All right. The reasoning is because here they tell you the mass cancels off in the equation. Here they tell you the mass cancels off in the equation. Plus, it makes no difference. Now, when do we see the mass cancelling off in the equation? It actually came from here. If you use the first method, you will notice that these mass terms here actually cancel off. So if originally you are using 230, 230, 230, they all completely cancel. Even if you were to change it to say 460, 460, or 460, they will still completely cancel. So no matter what max value you use, they will just completely cancel off. So it actually makes no difference. Eventually, you come back to this same conclusion where your actual centripetal acceleration is less than 9.8, you won't remain on the track. Okay. Now, there's also another answer here. This is also somewhat relevant, but I think this one is not so straightforward. They tell you centripetal acceleration is independent of mass, thus it makes no difference. This one would be related to this one. You see, the term for centripetal acceleration is v squared over r. There's no mass term there. So even if you were to change the mass, your centripetal acceleration is unchanged. It doesn't affect anything. Okay, so therefore it also makes no difference here. That's what we say lah. All right. Okay, so this is for vertical circle. If you look at the first page of the supplementary worksheet, November 4 P4, This one is number 4P4. They ask you to do some simple calculation. That one I think we can just very quickly just do it and then get it done with. Alright, so here they ask you, a particle is following a circular path and is observed to have angular displacement of 10.3 degrees. Express this angle in radians, show your working, and give your answers to 3 significant figures. Okay, so they want angle in degrees changed to radians. So this one we know usually you need to multiply with pi over 180. Okay, so if angle is theta 10.3 degrees, change to radian is multiplied with 10 over 180. It gives us 0.180 radians. This is in 3SF as what the question wanted. All right. Then after that, they will ask you determine tangent 10.3 degrees to 3SF. So use a calculator, find the value of tangent 10.3. You're going to get 0.182. Okay, again, this one it must be up to 3SF. Then last question. Hence, calculate the percentage error that is made when the angle 10.3 degrees as measured in radians is assumed to be equals to tangent 10.3 degrees. When they say percentage error here, you can just think of it as asking about the percentage difference. Okay, so there are two ways to do this. Either you take 0.182 minus 0.180 divide by 0.180 times 100%, giving you 1.11%, or you take 0.182 minus 0.180 divided by 0.182, giving you 1.1%. The only difference between these two is the value which you is the reference value you use to find the percentage difference. This one here is using 0.18. This one here is using 0.182. That's the only difference between these two. Both methods are equally applicable. Okay, so just use whichever you want. All right. Right, so the first two questions is about definitions again. So this one, they ask you what is meant by radian. It's asking you to define 1 radian, which is actually a unit. So this one I mentioned to you guys before, it is just the angle subtended at the center of a circle where the arc length is equal to the radius of the circle. Okay, so this one is very simple. And then the next one, this one is a bit different. They told you, why is it that 1 complete revolution is equivalent to an angular displacement of 2 pi radians? Why is it that when you go through 1 full circle like this one full circle is equivalent to 2 pi radian? Okay, so there was a derivation on the first page of your notes which I mentioned to you before. If you know the angular displacement is theta, or rather angle in radians, is your arc length over your radius, we know that for 1 complete circle, your arc length is actually the full circumference of your circle. Okay, for 1 complete circle, your arc length is actually the circumference of your circle, which is 2 pi r. So you sub it inside the equation that you have for angular displacement or angle in radians. This one will be 2 pi r divided by r. Eventually they cancel off, giving you 2 pi radians itself. So the answer was basically this. Theta is s over r. For 1 complete revolution, s will be 2 pi r. 1 complete is basically the circumference of your circle. So sub everything in, you eventually get this. Okay, so this is one part. Now B is the one that is the difficult one. Usually for standalone circular motion questions, they are not as complicated as this. This is the rare exception. Okay, most of the time in your circular motion questions, they are pretty straightforward. It's only this one that is a bit complicated. All right, so let's have a look at this. Okay, now here they tell you that you have an elastic cord that has an unextended length of 13 centimeter. One end of the cord is attached to a fixed point C A small weight of mass, of weight 5 Newton is hung from the free end of the cord. The cord then extends to a length of 14.8 centimeter. Okay. Now, one key thing to recognize here is that they mentioned that this is an elastic cord. Okay, meaning to say it can stretch. So when it can stretch, it actually behaves like a spring. Okay, if you apply a load onto it, the cord will extend under the load. So the subsequent description actually is telling you about that. They originally tell you that the unextended length was 13 centimeter. This one is when there is no load. But then after that, when they attach a weight of 5 Newton, a load is attached now to one end of the cord. The cord is actually now extended to a length of 14.8 centimeter. So this one is with load. Okay. So for now, just understand that your cord here is able to extend. It's actually behaving like a spring. Okay. We will make use of this information towards the last part of your question. Now, the later part of the question mentioned this. The cord and mass are now made to rotate at constant angular speed omega in a vertical plane about point C. When the cord is vertical and above C, its length is the unextended length of 13 centimeter. All right. So one thing to note here is that in the previous lesson, I mentioned to you when something moves in a vertical circle, I mentioned that their speed generally will not be the same. The speed at the bottom will usually be higher than the one at the top. But here, they've actually specifically highlighted to you, you actually have constant angular speed when you're trying to swing the cord in a vertical circle. All right, so this one, they've already specifically mentioned to you, you are moving with constant angular speed, or rather you're moving with constant speed. Okay, now when your cord is vertical and above C, the length is the unextended length of 13 centimeter as shown in figure 1.2. If you look at the next part of the question, sorry, next page, this is the diagram showing you what's happening now. The figure 1.2 is showing you the cord when it's at the top position. Sorry, when the cord is vertical and the mass is at the top. Figure 1.3 is showing you the cord vertical, but the mass is at the bottom. All right. Now, part 1 show that the angular speed omega of the cord and the mass is 8.7 radians per second. Okay. So in your case, it's actually up to this point here, they've actually only been describing this diagram here, where they tell you that the cord is vertical and mass is above the center of the circle, right? So it's better to analyze from this part only. All right. So you look at the diagram where I tell you this is the center of the circle, and then your cord is like this with your mass here. At the top of your circle, you can say that there is the weight acting on the mass. There's also the tension due to the cord acting on the mass. So this one here, my centripetal force is W plus T, which in turn will give me mr omega square W plus T. I already know that my centripetal acceleration is directed towards the center of the circle. So both these forces are in the same direction, therefore it is positive. Okay. Now, one thing to note here is this. Just now I mentioned to you that your cord is behaving like a spring, right? So your cord behaves like a spring. Just now one of the things I mentioned was that your cord behaves like a spring. Okay. So from here, if you know that just now they told you that your length of your cord is the unextended length of 13 centimeter, this one will actually tell you that tension is 0. Okay. Because the cord behaves like a spring, at the original unextended length, there is no force. Therefore, T is 0. Okay. Because if you say something behaves like a spring, we know that F is equals to Kx. This one is Hooke's law. So from here, F is actually proportional to X, whereas K is your spring constant, obviously. So if K is a constant, force will be directly proportional to your extension. All right. So if you're at the unextended length, that means your X is 0. Therefore, F is 0. Okay. So in your case, your F here is actually your tension in your cord, which will also be exerted onto your mass. All right. So here, that would mean that your original equation will now become this, no? mr omega square equals to W only. All right. So your full working is the one that is written over here. Right, at the top of the circle, W plus T is equals to mr omega square. Since your chord is at the unextended length, T is 0. And then your equation becomes W equals to mr omega square. W is just mg. Then you have mr omega square. The m's will cancel off, giving you 9.81 equals to 0.13 omega square. Then omega is 8.69 radians per second. And then you will get 8.7 radians per second. All right. This is shown. Okay, so this is all right. Most of the examples you've done so far that involves a mass tied to a string, the string is not extensible. It cannot extend. But this current question that you're doing, the chord is actually extendable. It can actually extend with load like a spring. All right. So that's the one thing about this question that is a bit different than the rest that you've done so far. Okay, so this one is okay. Then after that, we'll move on to part 2. Okay, now for part 2, they tell you that the chord and the mass, let me get rid of this. For part 2, they tell you that the chord and the mass rotate so that the chord is now vertically below C, below the center of the circle, as shown in figure 1.3. Calculate the length L of the chord, assuming that it obeys Hooke's law. Okay, so this time they actually ask you to consider the case at the bottom of your circle. So you're considering the bottom of your circle. If I tell you that this one is the center of your circle, this one is your chord, and this one is your mass, you still have weight W acting down on your mass, but then your tension T will be upwards right now. Okay, so your centripetal acceleration is towards the center of the circle. W is opposite to your AC. This is negative. T is in the same direction as your AC, your centripetal acceleration. So this is positive. Okay. Then from here, you just make use of the equation for centripetal force. Centripetal force here would be T minus W, which in turn would be mr omega square T minus W. Okay. Now I want to use omega here rather than mv squared over r because I already found out omega here. And you already know that omega is constant throughout your motion. So I want to use specifically omega. All right. Now, from here, you will need to start thinking about a few things. They are asking you to find length L. As it is right now, this expression does not have length L. You have to kind of change one of the expression inside here such that it's equal, such that it has length L inside. Okay. Now, remember just now I told you that your chord behaves like a spring. So, and here they already told you it obeys Hooke's law. So in your case, if you know that your chord behaves like a spring, you apply Hooke's law to the chord, tension is equals to K times your extension. All right. But extension itself can be rewritten as your length L, final length L minus your original length. let's just say your original length is L0 lah. Okay, say L0 is your 13 centimeter. The question already told you your unextended length is 13 centimeter. So if you know that your cord behaves like a spring, T can be represented as T equals to Kx, where K is your spring constant, and then your extension is basically your final length L here minus your original length. Okay, but then after that, you will also have another separate issue to deal with. You do not know what is K in the first place. You know L0 as 13. L is what you want to find, but K is also something that you do not know. So this one, you actually have to backtrack a little to what you actually read in the first part of the question. Now, in the first part of the question, they've actually already told you one information where they told you that with no mass, the extended length is 13 centimeter. Okay, this one is no load lah, right? Your length is 13 centimeter. But then after that, when you have a way of 5 Newton, your cord extends to a length of 14.8 centimeter. This is with load. Okay. Now, if I wanted to find specifically the spring constant from this information, you can find out the spring constant. You can actually just say that T is equals to Kx. Maybe I better just write at the top, at the side here. T is equals to Kx. In your case, your T, or rather your force exerted is 5. K is what you want to find. Your extension here is 14.8 minus 13 multiplied with 10 power minus 2 because you want to change from centimeter to meter. Okay. So all in all, your K is going to be 5 over 0.018. Okay, so you've actually tackled this part where you know what is K and you know what is L0. The only unknown here is your L. Okay, so you try to sub it back to your original equation. You're going to get mr omega square equals to KL minus L0 minus W. Then K in turn is your whatever values you have there. Right. So let me just show you the full working. So in your case, you just sub in everything that you know, right? In your case, if I sub in everything, M will be 5 divided by 9.81. Your radius is actually your L right now. Okay. Your omega is what you found at the top, 8.7 square. Then your K is 5 divided by 0.018 times with L minus with 0.13. 13 centimeter change to meter, and then minus off your weight of 5. Now, when you do all this, you try to solve everything. Eventually, you get your answer for L as 0.172 meter, which is in turn this one. Okay, next. So I'll give you guys a minute to digest and copy the workings. All right. Yeah, it's a bit complicated. That's the reason why this question is worth 4 marks. If this kind of question came out nowadays, usually they'll break up your question into a few parts. But in the old days, they tended to lump everything in one single question, and they expect you to figure out all the steps yourself. All right. This one is your R, but it's also your length M. Okay. That's why I can say this one is L. Okay, right. So with this, we are done with circular motion already. We've gone through all the questions on circular motion that are standalone. All right. Subsequent questions that you see on circular motion after this will usually be combined with another chapter called gravitational field, which is the chapter I'll be going through next. All right.